We've now looked at two different sections in the notes that talk about steady state error and evaluating it with respect to the reference input. Now we look at the steady state error with respect to disturbances. So recall again that system error is any difference whatsoever between the desired output of the system, R, and the actual output, Y. And so we've spent some time looking at differences between R and Y because the system is not capable of tracking R, and that's an issue with the closed-loop transfer function T. In the general case, or in the special unity feedback case, it's the issue with the open-loop transfer function. So if we want to improve the system type with respect to reference input, then we need to find ways to modify either one or the other of those. But there's another source of steady-state error, and that's uncontrolled inputs to the system, and those are what we call disturbances. And in the example we've talked about a number of times already, in a vehicle cruise control system, we might set the reference speed to 55 miles per hour, but we find that the steady-state vehicle speed is affected by wind and road grade, in addition to the cruise control system's ability to track the reference input. So the disturbance is going to have some impact on steady-state error. So when we're thinking most comprehensively about what's going on, we say that the output of the system, Y, has some transfer function T of S that multiplies the reference input, and there will also be some other transfer function TW of S that multiplies the disturbance input. So we find the system type with regard to the reference input by looking at the transfer function that connects the reference input to Y. And in a similar kind of way, we find the system type with respect to the disturbance input by looking at the transfer function that connects it to Y, which is TW of S. So TW of S in general is different from T of S, and we need to be careful to consider them both separately. So due to linearity, though, what we can do is we can evaluate these two problems separately, and that's nice. And so what we've done so far is we have ignored W. Basically, we've imagined W to be 0 and looked at what would happen with different inputs R. Now we are going to do the opposite and imagine that R is 0 and look at different disturbance inputs W. So when thinking about system type with respect to disturbance, we consider the reference input to be 0 and then follow the procedures on the next page. There's a big difference between what the system does with the reference input and what the system does with the disturbance input. We want the system to track the reference input exactly. We want the system output not to track the disturbance at all. The disturbance is an unwanted input to the system, and we don't want to be tracking it. So if there is any contribution of the disturbance in the output, that is an error due to the disturbance. And ideally we want that to be 0, but here we're interested in understanding what is the system type with respect to that disturbance. So the steady state error is equal to the desired output minus the actual output. And in this section, we're saying the desired output is 0. And so any actual output is error. And so the steady state error then due to disturbance is minus the limit as S approaches 0 of S times TW of S times W of S. Similarly to before, though, when we're looking at what types of inputs to consider, we might consider any old inputs, but we're going to look at the same categories. We're going to look at how does the system respond when there's a step disturbance or a ramp disturbance or a parabola disturbance or so forth. So there's a lot of similarities, but we have to be careful of the differences also. We say that the system is type 0 with respect to disturbance if it has non-zero steady-state error when the disturbance is a unit step, just like we said the system was type 0 with respect to the reference input if it has non-zero steady-state error when the reference input was a step. So those are the similarities, but we're talking about different inputs. That is, in this case, we have a constant non-zero, non-infinite value for ESS equals minus limit as s approaches 0 of TW of S would be a type 0 system. Similarly, a type 1 system, a system is type 1 with respect to disturbance if it has non-zero steady-state error when the disturbance is a unit ramp, 1 over s squared. And we would evaluate that as a type 1 system with respect to disturbance has constant steady-state error equals negative limit s approaches 0 of TW of S over S. We say a system is type 2 if it has constant non-zero steady-state error when the disturbance is a unit parabola. And so we have this formula here for calculating the type 2 system, the steady-state error. And so on and so forth. We would have a type 10 system if we have a finite value to negative limit s approaches 0 of TW over S to the power 10 in that case. So again, I thought it might be helpful if I included a summary table, and that is here. The system type with respect to disturbance is so the title of the table is steady state errors due to disturbance for generic closed loop TW of S. The system is type 0 if it has an error to a step input. It's type 1 if it has an error to a ramp input. Type 2 if it has an error, a finite error to a parabola input. Something to note is when we looked at system type with respect to the reference input, there were two cases. There was the general case, and then there was a special case for unity feedback. Now we're looking at system type with respect to the disturbance input, and there's no special cases for unity feedback. We always have to do the general case. So we don't simply count poles at the origin or anything like that. We must always compute the closed loop transfer function. TW of S is Y of S over W of S, and then perform the tests that we just talked about. As an example, we consider the motor control problem from before, and this is the configuration that we had. And in this example, we will use a proportional controller with gain K closed loop so that the control effort is K times R minus Y. And I repeat this example because we've done a lot of the work already, and we did all of the algebra of the block diagram and found that we could compute the output Y of S as some transfer function times R of S plus some other transfer function times W of S. And this here is TW of S, and this there is T of S. So we've already computed TW of S, which is what we need to compute system type with respect to the disturbance input. So there's T, there's TW. So starting with system type 0, we're going to test to see if we can find a finite non-zero steady state error. So here's our computation. Steady state error is negative limit as S approaches 0 of TW of S. So in TW I put S going to 0, that goes to 0, that goes to 0. I have numerator is B, denominator is 1 times 1 plus A KCL. I have B over 1 plus A times KCL, and that's not equal to 0. So we conclude that that system controlled with a proportional controller is type 0 with respect to disturbance. It turned out in this case it was also type 0 with respect to the reference input, but the two system types are not generally the same. It's possible to have a system that is maybe type 1 with respect to the reference input and type 0 with respect to the disturbance input, and so you can't just say one is the same as the other. So that concludes our chapter on looking at some basic properties of feedback, starting out trying to understand why feedback is of value. And we found out that it reduces our sensitivity to plant modeling errors. It reduces the impact of disturbance. It can change the transient response of the system because we move poles around. We looked at a simple controller design with proportional and integral and derivative terms, and generally speaking, what it means to add an integrator or a derivative to a controller, and even looked at the Ziegler-Nichols methods of getting a good starting point for what those parameter values should be. So hopefully by now you're beginning to get a pretty good grasp of what feedback is all about and why we do it and what it can gain for us. As we move ahead in the course, we're going to next look at understanding stability better, because that's a very important thing to guarantee in a control system. And after that, we'll look at some tools for analyzing and designing very nice generic controllers.